Davies. I lead our neuromorphic computing research program here at Intel. This talk is just a really quick overview, I hope quick, of the chip itself. We had this new architecture session scheduled today, so we figured we needed to say something about it. So this will focus very much on the chip. The main talk is Thursday morning, where at that point I'll give you more of kind of a broader sense of our motivation, our sort of approach to neuromorphic computing. We tried to develop Loihi in quite a principled way as much as possible, rather than just laundry list of features as we've seen in the neuroscience. But this talk right now may seem a little bit like a laundry list of features, intentionally so. So first, just one quick glance at what the chip is, and it's a spiking neural network chip, in case you hadn't surmised that at this point. We have a publication out, actually, at this point in IEEE Micro, so you can certainly learn a lot about the deep details that I'll just be covering at a fairly high level in this talk. It has 128 cores. It's a multi-core, fully digital, asynchronous implementation. Each core has up to 1,000 or 1024 neurons. So in that sense, it's similar to some other multi-core neuromorphic chips you may have heard about. There are some significant differences, though. We have a very extensive spiking neural network feature set, so I'll talk more about that in a minute. And quite significantly, we've spent a lot of time trying to develop scalable on-chip learning. And by scalable, what I mean is the learning rules are implemented in the same pipeline as the neuron model and the basic synaptic operation handling for inference, which means that as you scale up to more and more cores, more and more neural resources, the learning rules have no bottlenecks associated with them from an energy or performance standpoint. So figuring out the learning rules themselves, that's still quite an open, unsolved problem, as we all know. But at least the architecture supports the exploration of a principled approach to deriving learning rules and assuming that these lead to some kind of valuable technology. I should also say that at Intel, our approach to neuromorphic computing, it may go without saying, is to ultimately sell chips. So we're not developing these neuromorphic research chips to explore and study the neuroscience, although that's a very valid and very, of course, a very important vector of development. For us at Intel, ultimately, we're hoping this leads to new frontiers of orders of magnitude improvements in efficiency for emerging, challenging, intelligent workloads that, of course, we're seeing more and more demand for in the marketplace. We're not there yet, though, so Loihi should be very well understood. It's not a product. We're not selling it, although we are certainly looking for research partners to help us develop algorithms and software for it and applications. So as far as the feature set of Loihi goes, I'll come back to the fact that we have support for an extremely rich feature set, and in particular, the learning rules, as I mentioned, but also the scalability and the complexity of the networks that we support in terms of the fan-out degrees, the variation in fan-out from one neuron to a next. I'll talk about that more in a minute. As I said, it's a digital and fully asynchronous implementation, but fully deterministic too, which is quite important, we feel. Software development, algorithmic exploration, you want to be able to configure your chip at one point and have it march on exactly the same each time, at least for the foreseeable future. I think that's a highly desired feature, and we have that. It's fabricated in 14 nanometer FinFET technology. The synaptic operations and speeds are really not the focus of Loihi. The feature set and trying to get the feature set right was more the focus, but the numbers are competitive to what you'll find in other chips today, around 20 picojoule synaptic operation for inference, and about 100 times faster than real time when the chip is kind of fully loaded at its capacity. So if we dive down one step to the actual kind of architecture, the speeds and feeds, and what the architectural diagram might look like, we have it here. You'll see that, of course, most of it is the neuromorphic mesh itself. There's a single neuromorphic core, which is replicated, connected together through a network on chip. Network on chip has a huge amount of bandwidth compared to the spiking bandwidths we expect to see. Latency is really the more critical parameter of the fabric. We actually have two physical fabrics, which we can use both for spikes, load balance across them. It doesn't really matter for the spikes, but we have the two physical fabrics because we're sending management operations in band through this network, both for bandwidth and just for design simplicity. The whole design tiles together, so we can arbitrarily extend this up to a full reticle chip if we decided to do that. If there was some real application demand for that. Loihi itself is actually 60 square millimeters. It says 64 here, but if you measure the actual precise die, it's 60. There's 4 off-chip interfaces. So these are parallel interfaces so that we can extend the mesh in a hierarchical fashion. So we have a bridging function, so to encapsulate spikes for extending up to 16,000 chips, should we ever need to go that large. That is not, again, our focus at this stage, but some of our initial boards actually have 4 chips on them, and that's working just fine right back from fab. So. We also have what's we feel is actually very important, but an aspect that at Intel we may think about more than possibly others. We have embedded x86 cores, so standard processors, because there's only so much that actual fixed function neuromorphic cores can do. There's always some slow scale process that needs to be involved. There's initialization, there's encoding of data or decoding of spiking to standard formats, and that's best done in many cases as close to the neuromorphic computation as possible, not to have to bottleneck the system with off-chip bandwidth. So we have 3 of those processors in this chip, and there's debatable whether that's the right number, need more or less. So I'll talk about now one of the more unusual aspects, novel feature we have in the chip. So I said it's asynchronous, digital, and deterministic. That doesn't necessarily sound possible to some. So what we have is a synchronization mechanism, but implemented in a distributed asynchronous manner. So this is a barrier synchronization process. And so this is best illustrated in terms of how the mesh operates through in this kind of discrete time model of the spiking neural net function. So it starts, the mesh is completely empty and idle. There's some processing of the neural state for that particular time step that happens concurrently across all the cores. Based on the states of those spiking neurons, they may generate spike messages. These are packetized 32-bit messages that are sent along this mesh. There's no ordering or timing constraints whatsoever on the distribution of those spike messages. So, however, they do need to complete by the end of the algorithmic time step. And so there's this distinction between the real-time handling of spikes and distribution and processing of spikes and the algorithmic time step. So as all the cores complete their operations, shown in kind of the third block here, at least for 2 example cores, they're walking through all the neurons that they implement, they're generating spikes potentially. That's happening then for all of the neurons in the mesh. As the cores complete that time step's worth of work, they then generate these barrier synchronization messages, which they exchange with their neighbors, and through an emergent wavefront propagation, kind of roughly illustrated here, all the cores synchronize, but in a distributed asynchronous way. And that lets the whole system know that it's done with that algorithmic time step of processing, and it can now proceed to the next step. So what that means is if you look in time as how the algorithmic time is advancing, you'll have a variable stretch of time per time step. So this is a little similar actually to what you saw earlier with Simon Knowles at GraphCore, although obviously I would dispute the idea that this has to be asynchronous or that you need to strictly alternate between computation and communication. In this case, we preserve the need to have deterministic sequencing of the algorithmic time or units of work, basic blocks, however you might want to think about that, but we allow the communication to be interspersed with the computation happening in the cores within each time step. Okay, now moving down further to the core itself, this is just a pipeline diagram that mostly focuses on the memory structures in the core. I'm certainly not going to walk through this in great detail, but you'll notice immediately that this is nothing like a von Neumann architecture. There's no single memory and a single computational block. This is really a pipeline. It's a high-performance digital pipeline with asynchronous, so there's different processes that may handshake with the neighbors, and they'll take different amount of iterative time depending on the workload. One principle we followed here is these memories can be shared among the 1024 neurons or the up to 128,000 synapses that this core may implement. That gives us a tremendous amount of flexibility for trading off amount of features versus number of neurons, or how many synapses one neuron may require for a given network versus the average number. So in our analysis of the algorithmic space, that can be a very important thing. Too rigid an architecture can really compromise the applicability in terms of an algorithmic space. So walking through some of the specific features, this is the laundry list part, but I think for most of you, these should all be quite meaningful notions. The basics of it, we have a CUBA, LIF, leaky integrate and fire neuron model, discrete time, again, as I mentioned, but we have a synaptic conductance, and then we have a neuron membrane time constant. We also have, this seems to be quite popular these days, to go to multi-compartment dendritic tree structures. We support that, not necessarily because we see a lot of algorithmic need for it yet. I mean, hopefully there is some. The main reason we support this is because it's a generalization of multiple dynamic variables per neuron, in particular different time constants for synaptic responses. So if you want to have multiple synaptic ion receptor types, if you were to model that, you would use that in our terminology as multiple compartments. You can also construct arbitrary trees. You have nonlinear join operations supported, so there may be some interesting applications for that. It's a little more speculative. We have intrinsic excitability homeostasis process, so the threshold can adapt over time in response to the activity of a particular neuron's firing. We support axonal delays, so this is in line with this temporal computing, temporal coding approach. This is implemented as a proper buffer so that you can have multiple spikes in flight and you don't lose spikes. We also have refractory delays, of course, and we can randomize the refractory delays. There's other sources of randomness too that you can insert in the system, although refractory delays is a particularly efficient way to introduce stochasticity. And finally, on the output side, this would be all the neuron spiking downward that I'm walking through here. But on the output side, we have a 4K output routing table. And again, as I mentioned, you can trade off those resources. So some destinations can consume a lot more of that. Some neurons can consume more of those routes than others. On the input side, we have 128 kilobytes of synaptic memory that is almost arbitrarily shareable across different input axon distributions. So in other words, different fan-in for different neurons can have wildly different numbers of synapses and even synapse formats. To efficiently represent these networks we might want to support in the chip, we support a range of different compression types. You can think of them as being. So sparse, meaning that each individual list of synapses have an individually specified compartment that this synapse is associated with, to dense encodings, which are just arrays of start from this index, spool off to connect to all these downstream compartments. We also have hierarchical support, which is inspired from, say, the convolutional neural net idea of sharing weights and having a kernel that might be repeated over patches of an input, whether any dimensionality. We've generalized that, so you can have arbitrary connections between populations. You can specify a template connectivity in terms of populations, which you then bind to specific instances of the populations in the core. So that's a tremendous efficiency mapping efficiency improvement in many cases. We also support synaptic delays, which is far more powerful than axonal delays. There's the polychronous model of computing, or some of the results this morning we saw from Craig Vineyard for doing interesting temporal coding type of operations. To get maximal benefit out of that, you really need to be able to specify a delay per synapse. So we support that in addition to a weight. We have also eligibility traces, and this is inspired from reinforcement learning. So there can be provisional weight changes you may apply may generate, and then you store that in the synapse without actually applying it until some later time when you get some reward or punishment signal. But more generally than that, really what we have are a three-tuple synapse, where you have three variables, one of which is a weight, one may be a delay, or just another dynamic state variable associated with the synapse. And then the third is just purely a dynamic state variable associated with the synapse. So you can really start constructing learning rules, which I'll talk about in a sec, to implement arbitrary dynamical systems for each synapse in response to the network activity. So this can be important for things like the catastrophic forgetting problem. You can have inertial terms in your synapses so that you maintain some history of what the weight value should be until you have enough short-term evidence that you should actually start moving the real weight. So a lot of interesting opportunities there. For reinforcement learning, we have graded spikes. So this is, you can think of it as being kind of neuromodulatory type of things. So those embedded x86 cores can send these graded reward spikes, and they have some defined distribution within each core to a set of axonal synaptic fan-outs that might represent dopamine or some kind of a reward distribution. So all of that is useful for plasticity. That's really why we've implemented all these last few features I've spoken about. So here we have a flexible, but not too flexible, we hope. So the right degree of flexibility and programmability of learning rules that are associated with synapses and are expressed in terms of sum of products of some number of dynamic variables that are available to that local synapse. So of course, that usually means an input spike train filtered trace and an output, presynaptic, postsynaptic filtered spike train is really the language, the basic building block of our learning semantics here. And you can apply those learning rules to any of these three dynamic state variables, so weights, delays, or scratch variable. So a little more on that learning rule. We call it a trace-based programmable learning engine or architecture. And the important thing to recognize is that this is kind of the common denominator. I mean, anybody coming from the computational neuroscience side will know this well, that the real correct way to think about synaptic plasticity is not based on a delta t difference in spike time arrival and based on some lookup function you then apply a weight change. The biology, and really what is actually quite efficient to implement in hardware, is you have exponentially filtered spike trains, and there's some time constant associated with the decay of a spike that occurs either on the presynaptic terminal or on the postsynaptic terminal. Depending on the time constant of that filtering process, you can either look for very short timescale correlations in spike timing, which we call that then the traditional STDP and the B and Poo kind of anti-symmetric curve, or you can select very long time constants, and now you're expressing more Hebbian-style rate-based rules. And really the most sophisticated rules that we've seen, and we've tried to analyze ourselves, are mixtures of these. So a triplet rule, for example, incorporates some elements of short timescale STDP type rules, but also some longer time constant averaging to get longer temporal correlation. So a quick glimpse of the physical implementation. This is kind of what the chip actually looks like as you peer down. I mentioned it's, we could spend a whole talk just talking about the asynchronous design methodology that we developed for this chip, and this series of chips really. But it's effectively a highly automated flow. It's allowed us to do 4 chips in 3 years, basically, getting us to this point. It supports FPGA emulation, which allows us to, from this point on, be advancing the feature set and in a very incremental kind of agile hardware methodology and prototyping these things in FPGAs. And as you've seen, it integrates with the standard synchronous methodology. The x86 cores we have are purely synchronous and standard. Finally, this is just a mention to remind you to, if you haven't already, it was pretty crowded earlier, but we have some posters, we have some application demos in the room across the hall there. We also started working with Applied Brain Research just a little over a month, 2 months ago, and they've rapidly put together some great demos too that they're showing in there with actual low-E silicon. So that's it for now. Look forward to telling you more on Thursday.
Hello. Thank you for the detailed talk. I have a question regarding the scaling properties if you scale to multiple chips, and regarding this barrier synchronization process, because it's not obvious to me.
Right, right. So it's a very interesting direction. So barrier synchronization, as of now, it itself is a somewhat programmable process. So the simplest thing, what we've implemented, is just a straight extend the barrier synchronization domain. There are ways you can map that down and do it hierarchically in subdomains. What it would mean then is to send a spike some distance across multiple chips or different barrier synchronization domains. They must have a bounded amount of delay, right, in the algorithmic delay in the propagation. So there are ways to minimize that overhead of the barrier sync as you scale, but in a somewhat natural way, it requires greater algorithmic delay to implement that communication. But that's direction for future work, future iterations of the silicon, is to really realize that vision to scale up to thousands and of chips.
Thank you very much. Very interesting talk. Clearly, being able to do the training on chip is very exciting. But one question I was wondering is there an ability to load a pre-trained network in to bootstrap it, or do you have to train every chip from scratch?
Sure. Yeah. No, you can absolutely load pre-trained networks. And specifically, if you're thinking deep networks, there's a variety of research groups that have been looking into that, of how to train a deep network that's compatible with spiking models and to transfer that in a very deterministic and reliable way. In fact, Applied Brain Research, this is Chris Elias-Smith's company, it has done some interesting work, and that's what some of their demos are actually based on. So I encourage you to talk with them about
Cool. Just a quick follow-up. Could you take a trained network off of there, offload it, save it for another time, or load it onto other chips?
Conceivably. Well, certainly other Loihis, absolutely.
Right.
Yeah,
Yes.
yeah. No, there's absolutely, as I say, it's digital, deterministic. You dump the state, reload it, you'll get exactly the same deterministic behavior.
Great.
Very, very impressive. Thank you. So if you want to write values to details like the synaptic delay, the axonal delays, and other things, so there is like an easy programming language to be able to update these things, or do they have to do some value, or there are distributions over something?
Easy programming language that in the spiking neural network world, that's a difficult or a challenging thing to claim, I'd say. The software model is definitely still under development, so I'll talk more about that on Thursday. But certainly I would say the microcode for specifying those rules is very understandable. I didn't really talk about it, but it's just sum of products represented. You have some menu of different variables you select from, some constants to program in, and then you specify which variable to assign it to. So for sure that limits the scope of learning rules we can support, but it is a pretty broad range.
Thank you.
Sure.